Hey, Mr. B here. We're on to 1-3 equivalent expressions. Go through that. Just wanted to check in with you. Remember that you can write your name on the board with your topics if you have a question about a particular topic. Also, you'll see on the board there'll be some mini lectures that will be up there and a time when those will be given. If it's of interest to you, please show up. Remember on your assignments that the solutions are there. That's so you can check your work after you've done it. Some of you may have found that if you go and find a solution and write it down without really thinking about how to do the problem, then you haven't done so well on the mini quiz. If you want to succeed on the mini quiz, the way to make this work is to first do the work, try your best with it, then take a look at the solution set and see that you got it right, and if you did, great. If not, then what happened and why, and figure that out so you can succeed on that unit and move on to the next one. As I said, we're into 1-3. There's a few things we're going to do in this. This is about equivalent expressions. In this, there are a couple of activities. We'll go through those together. Then you'll also find that there is a guided example. I'll go through the guided example with you. Once we've done that, then I've got a couple of guided practice problems that I'll go through if you want to do that. Your assignment is covering the ideas and the applying the math. Once you've completed it, checked your work, then see me about getting your mastery quiz and getting ready to move on to the next lesson, 1-3. Now, before we get into that discussion, I did want to talk a little bit about another aspect of this book. You're going to find at the end of this is a summary and vocabulary section, which kind of describes what's going on in the chapter, the vocabulary for each one. Then there's a self-test. This is an end of chapter review to find out what do you know or not know. Take it like a test. Then when you're done, go to the back of the book and you'll find answers and solutions in the back to all of these questions. There's also a table that will relate the self-test questions to review questions that are available in this chapter review section. It's given by objectives as well as it gives lesson numbers. So if you're needing to go through this stuff, this would be the place to find it. This is the kind of work you're going to want to do when you finish all the units. You're getting ready to take the chapter test. Go through all this, do the review that you need to do to make sure you know the things that you think you know, so you can succeed on the test. Okay. Let's go through the activities in 1-3. You should be doing this yourself. Work through it. Try to see if you can do it. If there's other people working on this at the same time, get hold of them. Find out who. You could write on the board and ask for somebody. But compare your results. Talk about it. See what you can come up with. I'm going to walk you through it. You should have gone through this before looking at my answers. If you've not done that already, pause the video, go off and work on it, and then come back once you've had a chance to work through it. So here's activity 1. Welcome back. For activity 1, it's saying use the toothpicks to find out how many are used to make the patterns for terms 1 through 10. Well, we're given the first 4 terms. Term number 1 had 4, term number 2 had, let's see, the original 4 plus 3 more, so 4 plus 3 is 7. Then we took that one and we added another 3 to it, and then this one and we added another 3. So let's take a look at what that looks like. If you look at what I just lit up there, we have, as we go through this, we begin with the first term is 4, the next term is 7, 4 plus 3 is 7, 7 plus 3 more is 10, and we can go on down through the table to see that we end up with the 10th term is 31 toothpicks. Now this is useful when we're looking for a pattern to find out what's going on with it, how we might describe this as a mathematical sequence or pattern. For number 2, in words, we'll explain how to use the term number to find the number of toothpicks needed to make that pattern. For term number 1, well, what relates term number 1 and the number of toothpicks? We ended up with 4 toothpicks. For term number 2, we ended up with 7 toothpicks. For number 3, with 10 toothpicks. So what's going on here? If we use the term number, it looks like we've got something that is basically the term number multiplied by 3, and then add 1 more to that. So 3 times 1 is 3, plus 1 more is 4. 2 times 3 is 6, plus 1 more is 7. 3 times 3 is 9, plus 1 more is 10. So the nth term, if we were going to go through this, would be 3 times 9, that's 27, plus 1 more is 28, which gives us for the term number n, how many toothpicks are there? For the next one, use n to represent this. This is asking you to write an equation to describe this. Or write an expression, excuse me. An equation has equal signs. Expressions can stand alone. We don't know what they equal yet. So n represents the term number. And last time I used the example of 3 times 9. Well, 3 times 9 plus 1 worked. So for n equals 9, we can substitute then n for 9, and we get that 3 times n plus 1 is an expression that might work out to help us understand this sequence. We've got a table to fill out. You should have done this with your best effort. Term numbers 11, 12, 15, and 100. What was the calculation used? The calculation used is going to be whatever expression you came up with, and then the number of toothpicks is going to be what that expression equals. How many toothpicks are there? If you haven't done this, but now it might make more sense to you, again, pause the video, go work on it, come back, and then I'll walk you through the answer. Hi, welcome back, and here's the answers to that. 3 times 11 plus 1 equals 34. So in the calculation, 3 times 11 plus 1, number of toothpicks, 34. We'll do that for the rest of the table. You can see the answers there. If you need time, pause the video, write it all down, get it into your notes. Fifth one is we're going to compare some expressions. If you have a chance to compare to some of the other students in the class, that's great. If you don't have that opportunity because you're working independent of everybody else, you're not at the same spot, I've got a few for you to look at right now. And here's some that could work. One of the things to note is when simplified, in other words, like terms are combined, all of these are equivalent expressions. They all represent the same thing. Okay, that's activity 1. Let's go on down. We'll take a look at activity 2. Same thing here as with 1. Go through it, work through it on your own. If you have other people that are in the same place with you, go ahead and work with them on it. See what you can come up with, and then I'll walk you through this whole thing. Again, pause the video. Come on back when you're ready. I'll carry on with it. Activity 2, number 1. How many toothpicks are needed for the first term? That's pretty easy. We can count them. There's 6. How many for the second? We can count those. There's 10. If we build the third term, you could do this with toothpicks. You could do this with pieces of paper. A lot of different things that you could do to represent this, but how many do we need for the third term in this? And for the third term, there's going to be 14 toothpicks. So we've gone from 6 to 10 to 14. And now we want to try to describe this in words that allow us to determine about the nth term. In other words, by terms, what had happened. So it was the first term plus the amount we added. So we had 1, and we had 1, 2, 3, 4, 5, 6. And then the second term we had 10, so we had 4 more added in to that one. So 1 times something, probably plus something, is going to work. 2 times something plus that same amount should work. And let's see what that might be. For this one, we get as a sample answer, the two sides have n toothpicks, while the other two sides have n plus 1. So these two sides here have the n number, right? There's one toothpick, there's one toothpick. And these two sides each have two toothpicks, and this is one more, and this is 2 plus 1, 2 plus 1. So we've got a description of what's going on with that might help us. So we want to write an algebraic expression for that. It's n, but how many n sides do we have? We have 2. So that's 2 times n that we have there. So that's just 2n. And here we have an n plus 1 and an n plus 1, so that would be 2n plus 2. So we have, because we have 2 of those. So our expression is going to end up being 4n plus 2. 1, 2, 3, 4. That's the n value. Plus here we had our 2 more. So 4n plus 2. Okay, now you've got that. You've got a table to fill in. It's given you various term numbers and the number of toothpicks. Now you can see one of the things that happens with a pattern like this is when the term number is low, it's pretty easy to build the pattern. Not so easy when the term number gets high. If you have to use 58 toothpicks, this gets a little awkward. You might build it out, but it's going to take some time. So much nicer if we could calculate it. Now if you think 58 is easy, I can just keep going to bigger and bigger numbers till I find one that is so big you decide, no, that's going to take a long time and I'd rather calculate it. That's where math becomes useful. Here are the answers for the table. You should already have filled it in. You know what to do if you haven't done that already. So here we go. They're right there. Pause the video so you can make note of that. And then we're going to head on to the guided example on the next page. Okay, here we are, the guided example. This is talking about Alf and Beth and the discussion and the material up above. It asks you to compare their expressions for several instances. An instance is a specific use of a pattern. I plug in a number, I get a very specific result. A pattern is something where we have an n value. I haven't plugged in specific values yet. So I've got my instances, and here are the results for Alf. Are you ready? 1, 2, 3. What? No, you're not ready yet? Oh, well, pause the video, get ready, come back. Okay, thanks. Here we go. Ready? 1, 2, 3. There are your answers. This is for Alf's result. The bill in there is just, this is saying it's me doing this. Ignore him. That's Alf's results. Now I'm pretty sure you got Betty's, right? Yep. Okay, here we go. 1, 2, 3, and here's Betty's results. What we see is that for Alf and for Betty, we have exactly the same results. What that tells us is that these are equivalent expressions, because they've written different expressions. When we plug in different values, we get the same results, and they're equivalent expressions for what the results we've compared. Now it's possible that they would not work for other values. We could simplify Alf's expression and see whether it results in Beth's expression. If that's true, then we got something that works for everything. The next part is another example. You can work through this. I am going to go through an example similar to this one, different from it. You have this one to work on. If you want to hang around for the next example, please do so. I'll be getting to that in just 1 second. Okay, here I've got an example for lesson 1-3. You may have already, probably should have already gone through the example in the text. You have that available to you. But here's a new one. Suppose William and Kimia both wrote expressions to describe the same pattern. William wrote m plus 3, and Kimia wrote 4 minus 2 plus m. Are the expressions equivalent? One way to check and see if they're equivalent is to try something. In other words, try an instance of the pattern. So in this case, we'll go ahead and we'll try a value here, and we'll put it into both expressions and see what they equal. So for William's expression, we had m plus 3. Kimia's is 4 minus 2 plus m. So now if we substitute for these, that m equals 5, we can see what kind of result we get for both of them. In the case of William, we have 5 plus 3. 5 plus 3 equals 8. In the case of Kimia, we have 4 minus 2 plus 5, and that's going to give us an answer of 7. And with the answer of 7, that tells us for a same value of the variable, we get different answers for the expression. Therefore, we have shown through this counterexample that they are not equivalent expressions. That's all it takes to do that. If they come out differently, they're not equivalent. Just real quick, because I know you guys are all probably arguing about this, I don't know who's right, because I don't know what the original pattern was. So I don't know if William's right or Kimia is right. Given the available information, there's no way to know. We can just happily go on our way by saying they're both right if it were talking about completely different patterns. Well, that's weird. So somebody's right, somebody's wrong. I don't know who. Let's move on. Good luck with the assignment. Again, covering the reading, applying the math. When you're done, come see me, take your mastery quiz, move on to the next one.